motor controller techniques, you all know the basics of motor. So we will not discuss much on that, but yes, we will definitely see the fundamentals of the motors and motor controllers, right? So if you have any question, probably we can discuss at last, because again, we have to cover a lot of things in limited time periods, right? Okay. So what we are going to discuss is about the motors in the EV and the controller. So basically, we all know that you need to regulate the speed of the electric motor while it is in vehicle, right? However, we are already familiar with what type of motors and motor controllers are available. So not wasting much time. Now, as we know, motors are, are like, part of our life, daily life itself, right? Yeah, whether it is a kitchen or your fan or, your car, most of the, equipments or the in a daily usage, activities, we can see the motors, and without motor, probably those things might not be possible. So the electric motor is definitely necessary. And when we are talking about electric vehicles, it is the motor which drives your vehicle, right? So when we are focusing on the motors for electric vehicle, we have seen yesterday a few of the technologies of the motor, but at the same time, how this motor can run, that we are going to see, right? So there are different type of motors. Ultimately, the basics of the motor, the fundamental of motor remains same. That is basically, inducing an electric current and electromagnetic flux to rotate the stator and rotate the rotor. So basically, the motor. And what we are aiming to is that the electrical power will be converted into the mechanical power, right? Now, when we are focusing, uh, on a speed control segment, there are different types of motor based on the application available in the market. So we know the servo motor or the stepper motors, which we are using day by day, yeah, in our daily activity. But how those controls are being done, how the speed is being regulated, how the speed is being controlled in different type of motors, that we are going to see today, right? So in EV, we have different motors, but we will mainly talk about AC and DC motor. So AC and DC motor basically, they are being used in a various application based on the manufacturer's wish, I would say. Otherwise, any motors can be used. There is no specific requirement for any specific vehicle. Definitely the arrangement, the cost, the application of the vehicle, if we keep in mind, then the selection of motor becomes a crucial. Now, if you can see in this picture, the very first picture, top one and bottom left, so that is the motor which is being used in either vehicle, right? And you can see the arrangement of the motor in the vehicle. That is a motor which is called a PMSM motor, permanent magnet synchronous motor, and that has been given a belt drive to transmit the power to the wheels. Now, at the same time, in the middle one, if you can see, the center one, the white color bike, has a PMSM motor, but that has been powered by the chain drive. So the power is being transmitted to the wheels by the chain drive, while the motor which is there in the red bike, that is transmitting power through the belt once again. Yeah, and the last two one, the black Luna type vehicle and the bicycle, they are using a hub motor, right? So hub motor is basically the motor which is inside the wheel rim itself, and that is being used for a smaller application or lightweight application, you can say. They are also a BLDC motors, right? So different application, but the type of motor may remain same, correct? Now, the advanced application, or you can say the application in passenger vehicle or heavy vehicles or in the car, we have already seen the motor for Tesla Model 3, which is the right hand side. Yesterday we have seen the video of Tesla Model 3. So that is a sync RM, sync reluctance motor. Whereas in between, if you can see the old Mahindra E20 vehicle, if you remember, if anyone remembers that, so that is an induction motor which is being used on a rear wheel drive. The bottom one is also a three-wheeler that is called Arkimoto S. That vehicle also has an induction motor, but there are two induction motors which is being used in this vehicle, right? And the left one are the chassis or the open chassis of the bus and the truck, which has been shown here. The top one is of the truck and the bottom one is of the bus. You can see here the arrangement of the motor and how the motor is mounted on the vehicle. Now, these both motors are PM motor, permanent magnet motor, and they are coupled with a transmission system. You might have studied or discussed that particular topic in previous sessions, right? So you can see the size and different types of motor, how it is being coupled with the vehicle based on the different application and the various arrangement of the motor in the vehicle. Now, having said that, uh, the point which I want to clear out is there is nothing about AC or DC in terms of the location and mounting of the motor. However, the space requirement or the mounting requirement based on your application. For example, the bus and trucks are the heavy vehicles. They need to carry, a huge mass. Then it is good to have on the rear wheel drive. However, we already know that push is better than pull. So having a motor on the rear axle is always at a better side. But at the same time, the three wheeler which is being shown in the center part, that has a motor on the front wheel drive, right? Or there can be a motor on front and rear wheel drive, both front and rear axle, basically. Yeah. So any motors can be used, but then there is an application. There is a cost, and the requirement of the application at the on the vehicle. Now, the main difference between AC and DC motor. So while AC and DC motors are functionally, I would say, same. So ultimately, principle it is the same. They convert electric power into the mechanical power. But the only difference is the power which is being provided to the motor. One needs a AC power or AC current, and another one needs a DC current, right? So, and due to that, there is a difference in their construction also. Mainly, main components are rotor, stator, and the motor body. But for example, I would like to tell you here the hub motor which we have seen in two-wheeler. That motor is called a outrunner, right? So the rotor is outside and stator is inside. The shaft is static, or the shaft is steady because it is coupled with the swing arm of the vehicle, and because wheel rotates, that means the rotor is outside. So that is known as a outrunner motor. Otherwise, where shaft is rotating and the rotor is inside, that is known as a in-runner motor. But again, that can be AC or DC, anything. Right? The AC motor are powered with a alternating current and DC current, that we already know. But when we are using a DC motor, you can directly couple the DC motor with the DC power output. Whereas when we are using an AC motor, you need something to convert from DC to AC, which we call which we know, yesterday we discussed, that is known as an inverter, right? So the DC to AC power needs to be converted. Now, DC wounded field motors are constructed with the brushes and a commutator, which add to the maintenance, limit the speed, and usually reduces the life of expectancy of the brush DC motors, that we already know, the carbon brushes, to collect the current and then to run the motor. Now, in AC induction motors, we don't have brushes. There are only coils on the rotor and stator, and both are provided with power supply, or you can say the electric flux, and which creates magnetic flux in between, and it rotates. It starts rotating, right? And the main difference is the speed. The speed of the DC motor is controlled by varying the armature windings current, while the speed of an AC motor is controlled by varying the frequency. which is commonly done with adjustable frequency drive control. So you also know the VFD, right? Variable frequency drive, right? Variable frequency drive, VFD. VFD is the one kind of inverter. So that is the main difference, right? When in DC motor you are using current to be controlled for the armature windings, whereas in AC motor you are varying the frequency which is being used or being controlled through the drive control. So let's move to the AC induction motor. We already know the construction of the motor. It's a three-phase motor we are using generally, mainly or you can say the earlier adoption of the EVs were through the AC induction motor. They have good regenerative braking or regenerative characteristics. Yeah, they can work, better generator than any other motor, right? And when it comes to the road performance for the EVs, the AC motors can get better grip on a rough terrains also, and it can run more smoothly, which is more advantageous and beneficial, and it can give you the quick acceleration. Now, even though AC induction motors are more expensive than the DC motors, they are still popular to wider market and automobile manufacturing because it is ideal for the high performance cars. And definitely they can last longer because yesterday we discussed, right? If there is only a copper and the aluminum or the steel, ideally the induction motors are have infinite life, right? Those motors are most rugged motor ever. In industries, the induction motors are the only option which are being used nowadays, right? Right. So, what is there in the brushless DC motor? So generally, DC motor with the brush and brushless DC motor. So if we go for the higher voltage DC motors, probably the weight will be higher and the size of the brush will be increased. But at the same time, when we are having a brushless DC motor, they are very efficient and they need a very less maintenance, right? Definitely the weight becomes a challenge at that point of time, but the DC motor runs from generally 48 to 192 volt for the EVs. They have permanent magnets, which are basically the rare earth elements, and they use a magnetic field. Now, more car companies are also being have started using this PMSM or permanent magnet motor, or you can say BLDC motor, because of size and weight advantage. But here, when we are considering an application, uh, uh, mainly the things which are critical for this kind of motor is either the speed variation and the temperature with respect to the required power and torque. Now they are also being used nowadays in most of the electric vehicles. Yeah. Mainly in two wheelers nowadays, because induction motor you cannot use, or even if you are using, it does not make any sense. So the if you know the famous California based corporation, so that is nothing but the Tesla. Yeah, though Tesla started with an AC induction motor, but eventually, as we have seen yesterday, they are also switching to the sync reluctance motor, right? Synchronous reluctance motor. They are also using a permanent magnet motor, and which has given them a big cost advantage. And the efficiency and performance has given. It has increased drastically. So when we are talking about this BLDC motor and rare earth element, it definitely needs a very critical controlling system with respect to the current and the temperature control, I would say. Now, when we are talking about speed control of these motors, there are basically two methods, right? Phase control and inverter control. Generally, phase control methods are being used for single phase induction motor or AC speed control motors, like we have a fan at our home. But when we are talking about inverter control motors, they are basically brushless DC motor or three-phase induction motor. And you need to use either the DC motor unit or the inverter unit for controlling the motors. So how do we do the speed control for the AC motors? So, in general, the construction of the single phase motor is with windings at a stator and rotor. But at the same time, for the three phase induction motor, it includes a stator where the primary winding is wound on the basket shaped solid aluminum cast rotor, and the rotor with a low cost rotor will be the low cost because it is structured in simply like a cage form, and you can just wind your copper on the rotor, right? And it does not have magnet basically, right? So, how do we govern the speed? So, basically, a tacho generator is used to detect the speed, and it is attached to the motor as shown in the figure. As you can see in the figure, there is a motor, there is a tacho generator, then there is a control circuit with the capacitor, and you can see the power supply which is being controlled through the potentiometer, right? The tachogenator is made of a magnet connected directly to the motor shaft and stator coil, which detects the magnetic poles. That generates an AC voltage at 12 cycles per revolution. And since this voltage and frequency increases with a rise of the rotational speed of the motor is controlled based on the signal. So this is very basic controlling method. But let's see, we will see how the three phase motors and in EVs it is being controlled. The AC speed control motor has the features like the AC voltage can be controlled directly. The speed control circuit can be configured simply by smoothing the circuit, unnecessarily, which allows the compact design at a low price. In the same way, a long life design is possible for the AC speed control motor because a large aluminum electrolytic capacitors are not required there. uh, the switching is operated only one time each half of the cycle for the commercial AC power supply, which keeps generated which keeps generating the low noise, right? At the same time, for the DC motor, DC motor will have the connections like UVW or lambda configuration. The rotor will have magnets, like we have seen yesterday, they will be skewed inside the rotor. There can be a number of poles or the different number of poles, 2 poles, 4 poles, and mainly in the even number of poles. Now, inside the stator, there will be a whole IC, which is basically required to identify the position and the speed of the rotor, right? And the phase difference of the output signal from each whole IC will be 120 degree, which will be detected by that IC, right? So at each rotation, you will get the signal, what is the rotor position, and that signal will be given to the controller. Now, when that signal is given, what happens inside the controller? So the voltage control is realized by an inverter in the output part of the control circuit, or we can call it a driver. Now, this inverter generates a three-phase AC voltage from DC current by turning on and off, like the sequence which is shown in the figure below. That is basically a six switching element being used by FETs or the IGBTs, right? So basically, they are transistors, the switching unit, as we know. Now, what happens actually, right, in the power circuit? We can see this diagram, I'll explain. So the switching elements are connected to the motor winding as shown. Uh, the on-off state of the switching element determines which coil of the stator is energized, in which direction the current will flow, and which coil becomes north or the south pole, right? So if you have seen yesterday's video, the north and south pole will be keep on changing to rotate the motor because there will be a flux in between the coil and the magnets. Now, to do that, we also need to determine the position, what is the position of the rotor, and that has to be detected by the magnetic poles, right? So the whole IC will be doing that work, and the switching will be done through the switching on and off, giving a pulse to the FETs, or you can say IGBTs. So as you can see here, the 6 transistors are listed here on the left side. So when there is, I mean, north and south pole, the magnet, you can see the first column, number 1 column. When it is directed between U and W phase, the north pole is at U, and the S pole, the south pole is becoming a phase W. So transistor 1 and transistor 6 are on. As soon as they are moving to the next step, the transistor 2 and the transistor 6 are on. But if you can see there, the north and south pole is changing. This is just in transit, right? So the phase V becomes a north pole, but the W phase is a south pole, right? As soon as the power or the phase changes, what happens is the south pole remains, actually the north pole remains at a V phase, and the south pole changes to the U phase, right? And that point of time, transistor 2 and 4 is switched on. And on the third switching on, transistor 3 and 4 will be again on. And here, the north and south pole again inverted. The south pole becomes at a phase V, and the phase W becomes a north pole, right? And this whole sequence continues north and south, and based on that, the transistor 1, 2, 3, 4, 5, and 6, based on the given sequence, the sequence which you can see it here is is the sequence for the rotating the motor based on the UV and W. Now the UVW phase sequence is generally defined by the manufacturer. I want to call a U, V, and W as a sequence, but not necessarily. I can also call it a V, U, and W, right? Now, which phase comes first, that can be decided by the manufacturer. Now, why so? Because in this pair, right, U, V, W, uh, you will get 3 into 3. That is the position, north and south pole position. You will get U, V, and W. So there will be a 6 patterns which are right for the motor to be operated or to be running. There will be one condition where motor will be running clockwise, and there will be one condition where motor will be running anti-clockwise, right? So that changes based on the change of the phases and how you are giving a supply. Now, which phase or which sequence is the right sequence, that is being tested by when you are running a motor on a low load condition. The current will be the minimum to rotate the motor. When motor is running freely or without load or free running, will be given to the motor. The current used by the motor will be the minimum, and motor will obtain its maximum RPM, or maximum rated RPM rather, right? So that is where you can decide whether this phase sequence is right or wrong. And the switching, right, the switching will be done accordingly, and we already know the formula for the identifying the RPM, that is 120 F by P, right? So the frequency and RPM can be determined through that formula. Now, what happens during the BLDC control? So first, let us see the diagram. As you can see, there is a motor. Inverter is being connected. The motor is given a loop of the positional detection, that is with the whole IC. There can be, I mean, also one other sensor which is called a resolver, that can be also used. That detection is being done by the controller with respect to the speed detection, and that will be given given in the loop with the PWM setting, and again it will go to the inverter, and this closed loop will be continuously running as far as the power supply is constant or it is continuously given to the inverter, right? And the speed setting is nothing but you can control the maximum or minimum speed, say for example eco or sports mode kind of a thing. So that basically controls your the current which is being injected into the motor. Now the switching sequence. Of the inverter, which is decided by the signal from the whole ICs in the positional detection as a part of the as shown in the block diagram, right? The whole IC sends a speed detector, a signal to the controller, and it compares the speed setting signal in the comparison amplifier block, which then generates the deviation of the signal. The value of the motor input current is determined by the PWM setting and the deviation signal, right? So this will be a closed loop system and you can control your speed. Now, what is the feature, or you can say basically the advantage? So brushless DC motor units have the high efficiency because of the permanent magnet motor. Permanent magnets are used on the rotor, and the secondary losses are less. So basically, there are no windings on the rotor side, so there will be less resistance.
Hello. May I interrupt you, sir?
Yeah.
Hello.
Yes.
Sir, there is one question because we are controlling the induction motor with the inverter, and again we are controlling the DC motor with the inverter.
Wait, I'll come to that point. I know I'll come to that point.
Okay. Because what I am trying to say that because BLDC motor is again controlling like AC, na. So that my question.
No, I will explain. I'll explain. See, the motors, AC power which we are, injecting is basically to control the speed, right? Now, at a simpler level, you can think that for induction motor, right, that can be directly also controlled by AC power. Because we are talking about EVs that has a DC power source, that is a battery, right? And the BLDC motors which are running on a three-phase supply can be only AC supply and cannot be DC supply, right?
Okay.
So
Okay.
AC motor also needs an inverter when we are using when we are using a battery as a power source. And BLDC
Okay.
motors, because we are using at a three-phase input supply as a AC current, we also need an inverter, right?
Sir, my question
Okay.
is, sir, BLDC motor, how it will be run with three-phase supply?
If you don't mind, can we discuss
Yes,
at
sir.
the end? There
That
are
is also my question, sir. Because it is if it is a DC, how it can require this three phase now for means it is very similar to induction motor. Actually.
wait. We will discuss. Let me come to
Okay,
that
okay,
point. It is there.
okay, okay,
There are
okay,
many slides, more 20 slides I have to cover, right?
okay, sir. Okay, okay,
Yeah. Okay. So the rotor inertia can be reduced and a high speed response is obtained. It is possible to downsize the motor because it can have a high efficiency because of the magnets, right? And the speed fluctuation will the changing the load, sorry, the fluctuation while changing the speed will be lesser because of the magnets, right? Now, the main controlling types, or you can say the methods, trapezoidal, sinusoidal, and FOC. So that is nothing but the commutation methods for the motors. So trapezoidal, as we have seen, a six-step motor, sinusoidal, that is a sine wave control, and the field-oriented control or vector control known as a FOC, right? Now, each commutation method can be implemented in different ways depending on the control algorithms and the hardware implementation to provide their own distinct advantages. Okay, so trapezoidal communication or commutation, sorry. So this commutation is being done in a 6 steps. The method is very popular because of the simplicity of the control algorithm. There will be a 6-step sequence which are used by 3 Hall effect sensor to get the rotor position information, and it is the effective control motor speed, or you can say the controlling method for the speed control of the motor, but it suffers from the torque ripples during the commutation, especially at a low speed, and therefore it is a popular for low end application and requiring simple closed loop operation. So what happens is in trapezoidal communication, first of all, when you are using a magnet inside the motor, right, and the magnet and the pole pairs, right, the stator pole pairs, that creates a magnetic lock. So when magnets and the stator poles are at a 90-degree, then it becomes very difficult to rotate or to shift the position of the rotor from that position, and that is known as a cogging torque, or in simpler words, that is a magnetic lock. Right now, when we are using a trapezoidal communication, that works as a step control method, and the controlling waves are that creates a fluctuation, and so that is where you get a torque repulsion. Okay. Of course, those control is also, that is a non-linear control, right? Only 2 motor windings carry current at any given time, right? The non-linearity generated noise and vibrations. The current controller must be slow enough so that it does not react to the transition or transients from the current transfer from phase to phase. And that is where we have a limited performance. So basically, the speed will be also slower. Now, in order to generate a high torque with the trapezoidal commutation, 180-degree commutation method should be chosen, but the 120-degree commutation provides a minimum torque ripples. Now, why? Because at a 180-degree, the position directly changes from north to south, right? Which generates a very high repulsion. And that is where the 120-degree commutation is being chosen. So the distance or the rotation which is uh, you know which is going to be which will happen due to the this trapezoidal communication or 6-step commutation, that will be smooth, that will provide lesser ripples, right? Now, how it is being done, let's see in the next slide. Okay, so you can see this diagram. I'll explain. Okay, so the 6 operational modes are shown at a 120-degree commutation strategy, right, with the Hall effect position, which we already know. Now, each section has a 60-degree interval in order to conduct the 2 motor phases at the same time, and the switching sequence determined to conduct 2 motor phases consequently as the motor spins. So if you can see, there are 3 Hall sensors and 3 phase sensors, and the one 6-step commutation which we have seen earlier. So you can see the bottom one, the switches. Okay, the feds will be on and off based on the angles, right? So 120-degree angle. So when phase A is activated, right, you can see the Q3 and Q5 switches are on, and at the same time, you can see the position of B. B is a flat. So that is IA, IB, you can see, right? So the very next moment from phase A to phase B will be shifted. The quadrant changes, and the switching also changes from 60-degree. It will change to the 120-degree, and the Q1 and Q6 will come into the picture, right? When the phase B is energized. So eventually, the whole sensors 1, 2, and 3 will continuously give the position of the pole pairs, you can say, or the phase, probably phase position. and one by one the phase will be powered up, and there will be a rotation of the motor through the switching, right? So you can see from the 0, 60, 120, 80, the 360-degree rotation is achieved, and once that rotation is completed, again the same sequence will be followed, right? And this is how the rotation will be continued in a trapezoidal commutation, right? So that is nothing but the 6-step communication or commutation or the controlling method. In a sinusoidal commutation, the sinusoidal drive scheme replaces the flat peak of the trapezoid with a sinusoidal waveform, and that matches more closely to the back EMF. Now it is necessary to overlap the commutation of phases, selectively firing more than one pair of the power switching devices at one time. It can be operated as an open or closed loop configuration using a speed feedback sensor. And typically it uses the mid-range performance application, which is required a speed and torque control. So now sinusoidal commutation is more smoother or more, repulsion free than the trapezoidal one, right? And this can be a closed loop or uh, open loop also, but mostly nowadays closed loop system is being used to get better positioning of the phase or the rotor. Now the application of this sinusoidal is generally used in the two-wheeler application.
Does it
Whereas
have any polarity issues?
polarity issues as in?
In sinusoidal commutation, do we get any polarity related issues like that?
No. We will discuss if you don't mind, sir. We will discuss.
Okay. Yes, proceed. Yes.
Yeah. So the trapezoidal commutation you can use ideally for the three-wheeler, for example, or the slow-speed vehicle. And obviously, there will be a high load condition, and you also need a high torque. So when there is an application of a high torque, trapezoidal commutation or the controlling method is, I won't say preferred, but if you are using it, it does not uh, create any difficulties because you need a high torque and the speed is slow, so that can be easily used. And at the same time, it is easier method to control as compared to the sinusoidal one. Now, when we are going for a sinusoidal, mainly two-wheeler or the low-end vehicles are using this sinusoidal commutation, right? So what is the the block diagram, or you can say the sequence of that? So generally you get a current command that is basically a throttle input, which is given to the sinusoidal lookup table, and that is being so lookup table will have the data at which position or which degree, which rotation, how much current should be injected, right? And the whole sensor and encoder feedback will be counting that position continuously, right? And they will provide that position to the phase, right? And that will given to the phase commands to the different phases like A and B. Now that will be converted as a digital current lookup or digital loop module, which basically understands the how much current. So ideally the AC current is directly translated into the torque requirement, and torque requirement is nothing but the speed requirement, the speed increase, right? So that will be considered based on the various requirement, like if you want high speed at what degree of the throttle or the throttle rotation, and you can sync up that lookup table with the digital current loop, right? And alternatively, that will be given to the different phase one by one or based on the given sequence, and that will eventually convert as a motor output or the PWM output to the motor. And if you remember yesterday, we have seen that diagram, how this sinusoidal waveform is being created to drive the motor smoothly, right? So basically the sinusoidal lookup table provides a two sinusoidal phase current. In addition to the encoder, the Hall effect sensors are required for initializing sinusoidal commutation. The sinusoidal commutation modulates the three-phase motor current, which produces the smooth and precise motor control. It also eliminates the torque ripples and the non-linearities in motor current, which occurs inherently with the six-step commutation. Now we can see that diagram, what you are asking here. So if you can see this diagram, the polarity issues and all those which you were talking or you had a query. Now, if you can see this figure, the Hall sensors or the Hall signals and the back EMF waveforms are given for the PMSM motor. The back EMF VAB is in the phase with the inverse of the Hall B waveform. If you can see the A waveform, the top one, right? In the next waveform, the back EMF VBC is in phase with the inverse of Hall C, right? And then the back EMF of VCA or Hall signal A, that will be, so VCA will be in inverse with the Hall A. And the proper commutation of logic with the rotor position information provides correct switching sequence of the power switching devices. Now, this is basically, the MOSFETs will be keep on continuously switching on and off based on the given sequence, and there will be an overlap of two phase because you need to continuously rotate the motor, right? But it has to be very smooth and precise one. So the whole sensors will continuously detect your speed. It will give the feedback to the controller and which phase has to be energized one by one. That sequence will be continued to create this sinusoidal waveform. And generally, these waveforms are considered based on your total input or the load requirement, which also have detection based on the power and torque characteristics of the motor. And then based on that, the peak power requirement and the peak torque requirement is being designed to provide the right feedback to the controller, because there will be a demand from the rider or the driver as a throttle input, and that has to be converted in terms of the current, and which eventually will be converted in terms of uh, the on and off frequency, and that will converted as a AC current to the motor to drive the motor or to rotate the motor, right? Now, what are the advantages over the trapezoidal on the sinusoidal? So it requires a very high resolution position feedback devices, and optical encoder or resolver to detect speed and the position very accurately. Uh, which is basically a costly affair, or that makes this control method expensive one. But it definitely provides a ripple free, or you can say smooth drive, or the jerk free, or you can say vibration free drive. So that is where it is nowadays preferred for the high speed or the reliably or reliable speed like 40 to 60, right? And again, it is costlier than the trapezoidal, but you get a very smooth and continuous drive in this method. Next comes the field oriented control. It is a kind of a sinusoidal waveform control, but the FOC is suitable for the high-end application due to its complex design and the higher processing requirements. So what we discussed yesterday, integrated electronics, again, that comes into the picture. You need a very high-end and reliable components or FETs, IGBTs. It commutates the motor by calculating voltage and the current vectors based on the motor current feedback. It has to maintain a high efficiency over a wide operating range and allows, precise dynamic control for speed and torque. So the FOC is a closed loop system, and it needs a very, very accurate speed and position. In fact, the input from the driver to the wheels, what is going, that everything is being controlled very precisely to give the high-end performance or the very smooth performance, right? So if you can see this diagram, the current command or the throttle input is given basically to the filters. Generally the speed and the torque will be controlled based on the load, or you can say based on the demand, versus what is available with the battery, right? The current will be continuously being calculated in terms of DC to AC conversion, and that will be given to the motor based on the demand. Probably you can also consider the various other parameters like temperature derating, or the winding temperature, or the magnetic temperature of the motor itself, the board temperature itself of the inverter or the motor controller board, because of the high frequency, or you can say high switching of the IGBTs or FETs will create a very high temperature on the board, and that has to be controlled with respect to the various parameters, right? So the FOC is very complex one. Like I said yesterday, it can take I guess 1 million times in 1 second, right? Of the input, and it can also convert the data very precisely, right? So that is where FOC is complex and the costlier method. Now, what exactly is required for the FOC control? So the Clark transformation converts. So basically, which method is being used in the FOC? So the Clark transformation converts the three-phase sinusoidal system A, B, and C, or you can call it U, V, and W, in two-phase first. That is alpha and beta. That is, so names are just to give you the idea how it is being done, right? The two coordinate time invariant system E and Q. So D is a flux component and Q is a current component, is obtained by the Park transformation. In this system, the motor flux generating part is the D, which is a direct, and the torque generating part is a Q, which is a quadrant. The space vector modulation SVM provides more efficient use of the bus voltage than the conventional sinusoidal pulse width modulation, or you can say SPWM techniques. The maximum output voltage based on the SVM is 1.15 times bigger than the conventional SPWM. The SVM considers the power circuit as one device which affects all 6 power switching devices because it controls the voltage vector also. So if you can see the diagram, yeah, sorry, I guess we skipped this slide. So the FOC controls the stator current represented by the space vector. It transforms the three-phase stator current into the flux generating part and a torque generating part, which is D and Q, to control both quantities separately, right? The arrangement of the FOC controller resembles a separately excited DC motor. The various reference frame transformation in FOC are shown in the diagram. If you can see, the three-phase supply, or you can say the three-phase is converted into the two-phase using a Clark transformation. So A, B, and C, or you can say U, V, and W phase are first converted into alpha and beta, which are stationary to the rotating, right? And then the D and Q components are governed to make it a constant, right? To make it PC, or you can say to control the process of the two-phase system. So from AC stationary reference frame, it is converted into the DC frame, which is a rotating reference frame. Again, it will convert it from the Park transformation to the inverse Park transformation, and that will again go from D to Q into alpha and beta two-phase rotating system, and that will give you the space vector modulation once again, right? And which basically gives you the controlling of the two-phase system and then transforming it into the three-phase system. So if you can see the diagram left-hand side or the graph left-hand side, that is being converted in the FOC form at the end, right? Three-phase system. So you can see from the graph, the multiple switching or multiple or very high frequency, you know, controlling is being done in the FOC, right? So there we are controlling the flux as well as the torque separately, and that is where we call it a space vector or the vector control system, also like a field oriented. So we already discussed. So that is basically explanation of that image. So overall, the overall comparison of these 3-speed methods. So in general, for BLDC and for the PMSM motors, the trapezoidal, sinusoidal, and FOC commutation method are used. All has excellent speed control based on the application requirement. However, torque control for the low and high speed, if you can see in the trapezoidal, you get torque ripples in the low speed, and high speed it is efficient, because once you have overcome the torque ripples or the magnetic locking which we discussed, then once the rotor is in motion, the speed will be efficient, right? And it does not need very complex algorithm, and you can use a Hall sensor for the feedback. But at the same time, sinusoidal control system is excellent in the torque control, but inefficient in the high speed control. And you need encoder or resolver to sense the position and the speed, right? At the same time, FOC is excellent in terms of both high speed and the low speed, but it needs the costlier devices for the feedback system, current sensors and encoders. And the algorithms are also complex and very highly, complex algorithms which are required. Yeah. So overall, these three commutation strategies are being used for the motor controlling or the speed control in EVs, right? The trapezoidal commutation generates a torque ripples at a low speed and relatively efficient in the high speed range. Sinusoidal commutation provides a smooth operation at a low speed but inefficient at a high speed range. The FOC gives the best of the both trapezoidal and sinusoidal commutation with a smooth operation at low speed and the very efficient running at a high speed also. The torque ripples can be significantly reduced by matching the motor type with the commutation strategy. The adequate combinations for producing minimum torque ripple are the BLDC motor with the 6-step commutation and the PMSM with the sinusoidal commutation. The FOC can apply to both types of motor to get the best drive performance, but it may require an extra code or the complexity and the hardware. And the motor current waveforms are sinusoidal with both the sinusoidal and FOC commutations are required, right? So that's it from my side. We can go ahead with the questions, right? You can also refer to these two papers for your reference, the diagrams which we have shown. Yeah. It has a good explanation based on Park transformation and Clark transformation.
Hello.
Yeah.
Sir, that I was asked question 20 minutes back.
BLDC.
Because BLDC, we are controlling like BLDC like AC motor, and again we are controlling AC motor like AC motor. That was my basic
No.
question, fundamental question.
Yes. So
that
fundamental
was
question
not
is,
clear, sir.
yeah. See,
Because
in general, induction motor.
control
See,
method is required for BLDC as well as for induction, or any AC motor.
no. See, don't confuse yourself. First, let me clear two things. General induction motor, right? For induction motor, if you just provide positive and negative, can this motor run? Can you drive the motor?
Not at all. Not.
Not, right? Why? You need a starter, right?
Yes.
Why do you need a starter for the induction motor? I'm not talking about EV, general induction motor, fundamentally. What is the need of a starter for the induction motor?
These AC motors, these are called AC motors.
continuation,
These
for
AC
continuation.
motors will
No,
not
no,
be
wait. That's what you are coming to AC and DC directly. Let me talk
Yes,
two
sir.
different things. Wait. Okay, so induction motor we are using a AC, correct? That is what you are saying. And AC and BLDC motor, we are using inverter for both. So there is a difference. That's what I'm saying. Okay.
Yes.
So,
Yes.
so can DC motor run without magnet?
No. No.
Correct. So two fundamental with the DC in very first slide I told you. Induction motor or AC motor runs on a AC power. DC motor runs on a DC power. Is that clear?
Yes, sir. Yes.
Okay. Now in DC motor, if it is BLDC or brush DC, right? If there is a brush, you need a current collector in terms of a brush, right?
Yes. Yes. Yes, sir.
Correct. Now for DC motor, if you just provide positive and negative to the motor, it will start running. It will start rotating. Correct.
Yes, with
Am I right, wrong?
constant speed, na? Yes. Yes,
Yeah,
sir.
yeah. That's
DC
what.
motor
Now
will
you
run
are
at a
coming at the
constant
point.
speed.
It will be running at a constant speed. That DC
Yes.
motor will directly achieve its a maximum speed based on the flux generated between the magnet and the coil, correct?
Yes.
Based on the given input,
Yes. Yes.
right? So you will have a constant speed and you cannot control the speed. That is first thing. In that condition, the pole pairs will be
Okay.
limited. Now, I
Okay.
am removing brush. I am making it a brushless DC motor. But now I want to vary the speed. Once I can give a DC supply, it will attain a constant speed. But I want now a three phase. The magnet will remain same as a DC motor, PLDC motor. But at a winding side, I will wind in a three phase. Okay. And to
Okay, sir.
energize
Okay.
three phase, I will need
Okay.
AC supply. So BLDC motor also, I will use an inverter. Okay.
So the operation is looks like a AC. That's why that was my basic question. Means it looks like a
Yeah, but
AC motor,
why
na?
I now you understand why it is so? To control the speed.
Yes. 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 To control the speed, we require this inverter. Yes, I understand.
Yes,
Okay.
yes,
Okay.
and that
Clear.
is the basic difference. That is so BLDC we call it, but PMSM motor or PMAC motor, permanent magnet synchronous motor, we can call it a PMAC motor also. But ultimately AC, it is AC after inverter, right? The power source is definitely a DC. Whereas in
Means, sir,
induction
in a
motor,
Tata Nexon, because they are using a induction motor, na, in Tata Nexon. Again,
they have changed. They
the
have changed now. They
induction
have
motor is
changed
different
now.
from the DC. Okay.
Huh? Yeah, so earlier Tata Nexon and earlier Mahindra A2 were induction motor. Even earlier Teslas were also induction motor. You can check Tesla Model S and Roadster. They were using induction motor, right? So induction motor, the thing is the DC power is can be converted into AC. That is for sure. But you don't get instantaneous torque like you get in the PMSM motor with a magnet. Now, going with the magnet motor or the BLDC motor or the PMSM motor is the advantages based on the power to weight ratio of the motor.
Okay.
The compactness of the motor because of magnet is it can be achieved very easily, and you get a same power density in the compact size of motor than the AC induction motor.
Okay, I understood, sir. But operation-wise, what I feel that the BLDC is again it looks like a AC motor, na? Because we are controlling three phases again. We are inverting that DC supply. So
Yeah,
I
what's
found
wrong
that
with that?
it's like
So,
yes, it
yeah,
is
yeah,
like a AC motor, na? It looks like a AC motor. It is not
right,
fundamentally
right.
AC motor, but it looks like a AC motor. That
No,
was
no,
my
you are right.
basic question.
It is not looks. It is using a AC power to just to control the speed, and it is easier in AC rather than DC. In DC, you need to control the voltage. If you are providing constant voltage, then the power which is required uh, will be the constant.
Okay, sir, I understood. Very good, very good.
Yeah.
Okay.
Okay. Next.
Vagolikar sir, do you want to ask something? Okay, sir, there is one question in a chat
Hello.
box. I will.
Hello.
Yes, sir, please go on.
Can I ask, ma'am?
Yes, sir, sure. You can ask.
Sir, good evening, sir. Hello.
Good evening.
Sir, sir, actually, you are telling that it is a synchronous motor. You have told in the beginning of your lecture. In the synchronous motors are the constant motors. How it will be the speed it will be controlled. And the next thing here, in another question, probably in an AC sources or AC supply, there will be a huge amount of losses. It will be there.